So just a bit of a warning. We'll see how this works. I'm not. Hopefully this should come out. This should come out all right. But I didn't kind of completely prepare everything I wanted to, and so when I hit, I may hit some part where I'm not completely clear on what I'm doing. But we'll see. Okay. Okay. So what let's see, where were we? So let me kind of. Let me explain what we were doing last time and put this in and try and explain how this fits into this general context of what I've been trying to do since the beginning about this is really an infinite dimensional example of canonical quantization and the story about how canonical quantization works and what and given that and if you have some kind of symmetries on your phase space. So last time, let's see. So really what Here, this really is an example of canonical quantization. The symmetry group, and then a group G acting. Okay. And the Lie group G acting. And so, but what we're doing is we're really the starting point is just to take as phase space, or better think of it as a dual phase space, the solutions. So it's the real solutions to the Klein-Gordon equation. And if you want, I won't write down the Klein-Gordon equation again, but it's just that the thing you get that if you take the energy momentum relation, the relativistic energy momentum relation for a particle of mass m, and just change the momentum the spatial momentum operators to I times times spatial derivatives and the time and the energy operator to the Hamiltonian and the energy operator to I dt, and then you get the Klein-Gordon equation. But anyway, you can just think of it's just some kind of equation of motion, and it's got a lot of nice invariances. It's very invariant. It's going to be it's translation invariant. It's invariant under the full Poincare group of all Lorentz transformations and translations. Okay, and so then what you do so the way to canonically quantize a phase space, one way to do it is by the Bargmann-Fock method. What you do is you take this. Now you complexify. So you look at complex solutions to the Klein-Gordon equations. But then what you have to do is you have to break this up into using a complex structure. Minus, and so these are the things with positive energy, and these are the things with negative energy. Okay. So if you look at the energy is just the eigenvalues. Well, anyway, the energy are the eigenvalues of the time translation. You look at find the positive ones and negative ones. And if you want to if you want to diagonalize the energy operator, it turns out you have to actually work over the complex numbers. So this is complex. And so these are going to be the things that look like e to the minus I omega t, and these are the things that look like e to the I omega t. And so what you can think of then is m plus. You should then think of as a single particle phase space. Anyway, as a single particle space. So this is kind of the space of. You should think of this as the right analog kind of wave functions of a single particle, and then minus is related to this guy by conjugation. That this space is always contains whatever is in here that has positive energy, or that has just taking I to negative I takes you from here to here, and so it's the conjugate space. And as I explained last time, this is a little bit different than what happened in the how we did this in the non-relativistic case. The non-relativistic case, we didn't really have anything like M, but we just had that H1. That H1 was the solutions to the Schrodinger equation, and they were all positive energy. And then H bar 1 would be the conjugate solutions. Okay. Then and then what we're going to do is to quantize this is really just take as our full state space the Fock space based on this thing, which is you just take the symmetric algebra of this guy. In other words, you take essentially just all possible tensor products of this guy over the complexes, and that's the kind of n-fold tensor product will describe kind of n particle states. And then what's going to happen then from the quantization here? Okay, so on elements here were these solutions. So they're going to get, these are the analog. These you should think of as the analog of what you had in the finite dimensional case with these Q's and P's. The Q's and P's were the basis elements in here, and that they got quantized to operators which acted on the state space. And in the so one thing that's going to happen, which we'll see, is you're going to get solutions here are going to go to operators acting on here. Solutions to the Klein-Gordon equation. Elements here are going to go to operators acting in here, which are going to be field operators. And in particular, you're going to have in the Bargmann-Fock picture, you're going to have kind of, if you've broken this up into the analog of Z and Z bar coordinates, and you're going to have creation and corresponding creation and annihilation operators, and those are going to act on this Fock space, and they're going to take you up and down in the number of factors you have here. So that's generally what's going to happen. So the next thing we need is we need to explicitly kind of get our hands on what solutions of this look like. And so what I did last time is I showed solutions look like. Well, one way I wrote them last time was that they looked like phi of t x vector is an integral. Well, for various reasons, you use this normalization. Then the integral over R4 of FP T0 T for. And so we talked about this a lot at the end of the last class. That this is just kind of a relativistic invariant way of so you just pick any kind of function of the form momenta, and then we restrict it to the the positive energy mass shell. And I guess you needed you should also say you better restrict the positive. No, sorry. Yeah, I don't want that yet. Sorry. So you restrict to the mass shell, and then you get something that only depends upon the values of this guy at on the mass shell, and you can then think of you can label your mass shell by just by the spatial momentum corresponding to the point down there, and then then you can rewrite this thing as this way. Is it alpha of P vector e to the vector T. Sorry, space here, and then there's that term, and then there's a PT minus IPX. Yeah, sorry. Okay. Anyway, this is all stuff that I did last time. Oh, sorry. And then there's this, and then there's an overall factor. There's an overall factor here, 1 over 2 omega p. And it's this guy divided by this guy. Oh, sorry. And then in the way of normalizing this, it's this 2 omega p. Okay. And this guy is explicitly Lorentz invariant. This guy is not obviously Lorentz invariant, but he comes about from integrating, from using a delta function to change from a 4-dimensional integral to a 3-dimensional integral. And you're done. And then the other trick here was a normalization, with the way I had to explain that I used. Anyway, let me not write that down. But there's to get from here. So this guy is really, so alpha of p vector is really this guy on the positive mass shell divided by the square root of 2 omega p, and this is this guy on the negative energy mass shell, again divided by the square root of 2 omega p. Okay, but this is just different ways of writing out solutions. Now okay, so now how do you? Okay, so there's 2 different ways of Let me say this here. I want to do this. Okay, so 2 ways of writing. Okay, so H1. So here. Maybe let me just do it this way. So here. So H1. Vector. So it's the set of functions on R3, and then there's the inner product. Alpha 1 of p vector. Bar. This alpha 1 bar, alpha 2. Okay. So then it's just the usual inner product. So you can think of, so this is one way of explicitly thinking of what the space is. And then H1 bar is just the complex conjugates of these things. And you might want to worry about exactly what kind of what we're doing here now is basically saying that you're going to think of these things maybe as L2 functions. Again, there's similar issues about kind of making this rigorous, which arise here. That you really, if you want to think about an actual momentum eigenstate, then you need this guy to be a delta function at a certain p vector, and then he's not normalizable. So you have all the standard issues about do I want to think of these as being L2 functions, or do I want to think of it as being really not having a story about really nicely behaved Schwartz functions and about distributions. So in general, I mean that same problem occurs here, but it doesn't. There's nothing really new about it from this point of view. But you have to worry a little bit about exactly what this means. What version of this are you getting? Okay. What do I want to do? Let's see. So the next thing I think I wanted to do, I realized, was to tell you about. Okay. So now, or. So there's really kind of two different ways. And there's another way of thinking about this, which is to if you're in X space. So this is really the nice thing if you're in P space. If you want to work in momentum space, which is what you must normally want to do, then you want to think about this as being an infinite potential space with, which is really just the functions at all possible values of p. But if you want to, the problem with quantum field theory is that you don't want to just stay in momentum space. You often want to think about what's happening in position space. And so if you want to get fields, if you want to think about how to parameterize the sky in position space, or you can take H1 is equal to the set of, well, what you can do is take now, if you want to describe a solution of the Klein-Gordon equation by using initial data at time 0, you would have some kind of phi of x. So this vectors. So this is the field at time 0, then pi x vector. So this is going to be d dt x vector. And no, so what I can do, and anyway, I won't try. You can figure out what the corresponding what the corresponding how to write the inner product in terms of these guys. I won't try and write that down. Or you can see how to do that in a minute. But the idea is that this data is kind of one complex value. So this is a complex valued function on R3, or two real valued functions on R3. And it's really kind of the same story as with the harmonic oscillator. Here, this is the analog of your Z, and this is the analog of your Q and P. So you've got Z's. You can describe the phase space in terms of Z's or in terms of Q's and P's. And the formulas that you end up writing down are really just kind of infinite dimensional generalizations of what you would write down in the harmonic oscillator story. Okay, then how to get, now let's do the quantization. Okay, and then quantization basically starts with this thing, and the idea is that if you have this kind of inner product, if you've made your H1 into a complex vector space with this kind of inner product, then you can do canonical quantization with kind of annihilation creation operators with the standard commutators corresponds to using the standard inner product here. So quantization of this in this picture looks like this. What you want to do is write up phi. So you get an operator like this, depending on time space, which is the integral over R3 of now a dagger, a p vector, e to the omega p vector t, x vector, and then plus a p, p, and then p, u, p. Okay, so you can write at the field operators as basically a kind of going back to anyway. This is so going back from these solutions in position space, which you now quantize into operators, to something in momentum space, to something in position space, and it's an operator. So this is the way you write the field operator using in that. And these guys have these standard A of P here. Okay. So this is the this is what you get, and maybe something to notice that's a little bit funny about this whole. There's something funny about working with these relativistically invariant theories is that it's built in. Is that you actually have, you know, when you write the field operator this way, like this, you know, time dependence is being treated very much like space dependence. So the anyway, let me say a little bit more about that later. But anyway, but you're actually getting the solutions at all time. Okay, then maybe the other thing that I wanted to say was that if you wanted to go back, or let's do this one. So that's using this guy, or to, so we can figure out how to write these guys. And the way to write these guys is just well, it's the same. Oh, okay, so if we want to write these guys, actually maybe a better, maybe I shouldn't have said it this way. Yeah, sorry. So let me just say that what I want to do is I want to get so that's this, and I want to get what is pi, and so pi is just going to be ddt of this guy. He's a corresponding velocity. So if you just differentiate this guy with respect to time, you get pi hat of t x vector. What are you going to get? It's minus I omega p vector, and then p vector. Oh, actually, sorry, let me do this. Yeah, let me say this a bit differently. Sorry. Okay. So your operators are going to correspond to the you know, to basis elements on your on this space, and so on. Yeah, this is sorry about this. This is really not what I wanted to do. Okay, so let me do it. Right. So one. So what you have is that you have operators. So what I really should be doing, I'm getting confused here about trying to tell you about time-dependent operators, which is kind of an analog of a kind of a Heisenberg, these Heisenberg operators that evolve at all the time. But it's better to be clear about what we're doing, to go back to the analogy just with a standard harmonic oscillator. What I really should be doing is I should be telling you just what's the analog of a Q and what's the analog of a P and what's the analog of a Z and a Z bar. And this is right. So here it's just, these guys are just the Z and the Z bars, and these correspond to, yeah, anyway, so you have, let me just say it this way. So you have two, ways of it. Anyway, you have either. Well, you have two pictures, two things related by Fourier transform. Okay, one is the dagger of P vector A, P. So this is your analog of your Z and Z bars. And the other one is the analog of your Q's and P's, but these are going to, these correspond to these solutions at T is equal to 0. That's where I'm trying to, I don't really want to talk about the Q, what Q of T was in the harmonic oscillator case. I wanted to talk about the operator Q and the operator P, and you could think of those as being, in the Heisenberg picture, those are just what's happening at time 0. So those would correspond to the T is equal to 0 value of the field, and so the T is equal to 0 value of the field is this. That's 1 over times then A dagger e to the I P vector dot X vector and then you're going to have a d cubed P vector over square root of 2 omega P. So this is just the time at the T is equal to 0 version of that field operator that I talked about. And so this is good. So you're going to have these guys. You're going to have this pair of adjoint operators, which is very similar to having what happens when you start with a Z and a Z bar in the Bargmann-Fock quantization. Or you're going to have an analog of a Q and a P operator, which here would be so pi of X vector. And now I'm going to do, and this is what you get by taking the time. Look at the formula for this thing in terms of that has knowing it's, where you know it's time evolution, and then take the time derivative of that, and then you end up with that thing I started to write before, 1 over 2 pi. R cubed. There's a minus I omega P vector, and there's an A of P. I got this right. A of P e to the I P. Now I'm confusing. Did I do this right? Sorry. Yeah, sorry. This should be this. Sorry. I got. And then there's a plus minus A dagger of P. And now I'm just not. Oh, okay. So the I omega P is the whole thing. Okay, so I hope you can read this. But this guy is what you get by taking that formula I wrote down for the field operator at all times, evaluating at T is equal to 0. This is what you get by taking the time derivative of that and evaluating at T is equal to 0. But in order to kind of, what I was trying to do when I was writing a lot of this was then try to write this thing down, things down in a way that you could then go back and look at the development look at how you would do things for a harmonic oscillator with an arbitrary number of components of degrees of freedom, and then just do this do exactly the same things here. And so, but instead of having Z and Z bars and A daggers, which were indexed by some index that took a finite number of values, they're going to be indexed by this continuous index, the momentum P. Or if you take the Fourier transform, then you could think of it in terms of something that's like a Q and P. So an analog of a Q would be this thing, and an analog of a p would be this thing. And these q and p operators were are indexed by the position space. So anyway, that's so both of these things are useful. So when you're doing computations, it's, you know, if you want to, if you can work in momentum space, often things are very simple, and then you just need to use these operators. If you want to work in position space, if you want to talk about what's actually happening at a certain position, you have to start invoking these operators, and then you so these guys satisfy this thing, which is kind of the quantization of what you would get from a Poisson. You know, you can write down the correct Poisson bracket for the alpha of p's and the alpha bar of p's. Then these guys are going to have another. So let's write down there. So these guys are going to have commutation relations. Where are we? Phi h. Hat. I. There's an I. And then the other ones, the pi, the phi's at different x's commute with each other. So that's kind of crucial, actually, is the phi hat of x is equal to 0. And again and same thing for the pi's. So these operators here are kind of you should think of they're kind of that's saying that at a given time you've got this infinite number of operators at each point, and they're all commuting with each other, so they can be simultaneously diagonalized, you know, at a given time. But the thing which is tricky about this is that these are really distributional. Really, if you want to make sense of these things, you really these are just kind of formal things that really make sense is kind of integrating this guy against some Schwartz function, and then you're going to get some well-defined operator, and you can figure out what if you do this for two different Schwartz functions, you can figure out what you're going to get here. You're going to get the kind of the inner product of the Schwartz functions there. Okay, so that's that. Now, what else did I want to? Okay, so then the okay, so then now let me get started a little bit on the issue of symmetries. So. Okay, so the point is that various groups, Lie groups, act on so the various Lie groups that whose action commutes with the Klein-Gordon operator, and which which take the solution space to the solution space. So they act, and then they act on H1, and especially the one we're really interested in this case, the Poincaré group. So in some sense, I mean, I guess what I wanted to say before is that in a lot of these non-relativistic cases, what you had was you had various groups, like you had spatial rotations acting, and you had you had kind of time, and then time translations. The actual time translations was something separate that gave you the dynamics. Here you have this overall group of space-time transformations, which is going to include spatial translations, which are going to give you the momentum operator. It's going to include time translation operators, which are going to give you the Hamiltonian, and it's going to include rotations and boosts. So you want to kind of find out how is this group going to act on the states of this quantum field theory. And but one thing that's a little bit that's kind of different about the special relativistic case is that the Hamiltonian and the momentum operators are just different components of the same kind of four-dimensional thing. So the fact that saying that this thing, maybe I guess the thing to say is saying that the Poincare group acts on this problem, automatically includes the dynamics. So this includes the dynamics. Because this also tells you how these things are going to. It also tells you what's going to happen as you move in time, which is it. And then so let's see what I wanted to do then. Okay, let's go. Okay, so what I was trying to do, and what I tried to do, I think was only kind of partially successful in writing the book, was then to try to just take exactly everything that I'd done. So recall, well, anyway, in the finite dimensional case. Yeah, so for M finite dimensional, and what I did was we had so Lie groups G acted on M, preserving the Poisson bracket, and so G was a subset of SP of 2D. Okay. So what we always had, and then the game. And then, so what we did then is what we found for each, let's say X element of Lie G, you get a quadratic function u sub x on M, and when you quantize, and you get a quadratic operator later, and depending on whether, and you could do it in the Bargan-Fock thing, yeah. So in the AJ dagger AJ or QJ PJ or QJ PJ. So I developed a lot of, kind of went, probably spent far too much time kind of developing formulas for how you would, if you had some kind of Lie group acting on your phase space and it preserved the Poisson bracket, how you would, and this is kind of the analog in this formalism of what you often do, people do in physics often do using Noether's theorem, is how would you, there's some corresponding quadratic function on M, such as, and this, which is sometimes called kind of the generator of the symmetry. It's that, you know, Poisson bracket by this guy gives you the infinitesimal change of your Poisson bracket of some function by mu sub x. Yeah, so it's just so roughly, well, anyway, Poisson bracket by mu sub x, Poisson bracket by mu sub x of a function is going to be infinitesimal change in the function. This was, I don't want to say more, you can say more precisely what this means, and if you look at the definition of the moment map. And then when you quantize, you had an operator, which was the algebra representation operator for some unitary representation of the group on the whole state space, and then this on other on other operators. You know, on, let's just say on your Q and P, or on your A dagger A. On one of these was again the infinitesimal in, you know, in a corresponding, you know, in QP or, you know, ZZ bar. Okay, so this was, anyway, so this was the general principle kind of used to get to get these quadratic operators. And there's a bunch of formulas about how to find them, you know, given explicitly the Lie algebra and how it acts on M. Okay, but what I want to do here, okay, and so here the plan, maybe the plan. What are the quadratic operators in phi hat, or a dagger A that for x element of the Poincare. So if we've got some kind of something in Lie algebra Poincare, it's an infinitesimal translation, infinitesimal rotation, infinitesimal boost. What there's some kind of corresponding operator, and you'll be able to write it in terms of, you know, in terms of the X space operate field operators, or in terms of, if you like, of the P space field operators. Okay, and maybe the and there's something I should actually say. Well, let's actually say in terms of this guy, maybe it's better to just write down the answer, because the answer is actually more obvious than any derivation that I can give of it. And so what's going to happen is that if for a vector is equal to spatial translation, so infinitesimal. What we're going to get is we're going to get p vector is equal to just the integral over r cubed of the p vector times a p. Okay. So this is small p vector. Okay, so I can go through that whole formula. You can go through as an exercise in the whole formalism of, you know, of trying to say what's an infinitesimal spatial translation and what's it going to do. but what it's going to give you is going to be some, so corresponding to some, what's going to be generate infinitesimal translations is a quadratic operator in the A's, which is just this obvious thing. It's just the thing which basically you're thinking of these. If you actually had discretized your momentum space, this would just be a finite sum, and you're just summing the number operator for the momentum corresponding to for the index of the momentum p. You're just summing that overall momenta, and then related by and then multiplied by the momentum corresponding to that state. So you're gonna this is just telling you how many. This is just going to have eigenvalues telling you how many quanta there are of momentum p. You multiply by the momentum p, and that gives its contribution to the total momentum. And then similarly, for time translation, H. Now the operator is the Hamiltonian, and we'll call it H hat, and that's the integral over R cubed. And then it's this, you do the same thing. Integer of P, A of P. Okay. Anyway, so I think what I'm going to do is, what I wanted to do then next is to kind of to get to cases where you're not where things are not going to be diagonal in this P representation, and then you have to do more work to figure out what the quadratic operators are. But I think let me leave that for next time. So next time, let's see, find these for well, let's actually next time we'll do the actually I shouldn't say. Well, anyway, next time let's do rotations and boosts, and then also in terms of okay. So you can see the kind of the rest of the story that I should tell you before I finish this, and which I think I'll leave for next time so I can do it. Make sure I'm a bit better prepared and I've got it right. Is that is to answer the question? Okay, well, how do I write down formulas if in X space in terms of these two operators for the momentum and for the Hamiltonian operators and some quadratic operator in these guys, and how do I find the operators for rotations and boosts? And then there'll be one other thing that we'll do next time is to talk about, what if you have if you start out with complex scalar fields, and then they're going to typically have a symmetry of rotating the complex coordinate by e to the I theta, and what quadratic thing do you get for that? So that's for next time. Okay, so let me stop it. But this, yeah. So so apologies for not giving a first principle derivation of this. So for what I do next time, it'll be a little bit easier, a bit more clear how to.
Just to make sure, so the P and H are coordinate relevant or irrelevant?
Are what?
Do they rely on the coordinates or?
Wait, but which these form? But do you understand these formulas? And actually, let me say then that one thing you can do is to check that these are the right. Maybe I should have said this is to check that these are the right formulas. Yeah, so you can calculate. Let me see if I get this right. where are they? There's one last thing I'm going to say. This, and we can calculate. Yeah, D. Well, anyway, it's going to be I. You can calculate. You can calculate. See what H hat does to phi hat, and you'll see that if I got this right, so there should be a minus psi I d phi hat dt, and then t vector is equal to minus I okay. Sorry, that was just the last thing I wanted to say. To check one thing to check that these were actually the correct. You could check that these were actually did what I said that they would do. Is that they're quadratic operators that if you calculate their commutators with the field operators, you get infinitesimal time translation or infinitesimal spatial translation. Okay. But Chilin, what was your question? I'm sorry. Does that answer that, or did?
Yeah.
Okay. Okay. Yeah. So anyway, but this was the whole. As I said, this was kind of the game, was to find something that did this, and I was kind of, instead of kind of taking the formulas that I kind of written down for the finite dimensional Fourier finite dimensional harmonic oscillator and computing with them and finding how they worked in infinite dimensions. I was just writing down physically what I thought the answer had to be, and then checking that was the right thing. A little bit about okay. So as I said, so next time let me go to we'll do this. We'll do some more. We'll finish the story next time, but you can see what we want to do is I want to get the rest of the Poincare-Haley algebra, not just the translations in space and time. And okay. So now what I wanted to do this time, let me start on this, and this I think I may just have time to start on and finish next time. Was the okay? So the computation was called the propagator. Okay, so the propagator. Okay. So this is the thing that is supposed to tell you that if you create, so let me actually first, so let me actually, well, I guess I'll say what I want to compute. So we want it's going to be thing that you start with a vacuum state, and then let's see, where did I want to get this calculation right? Where was it? Okay. So, and now I wanted to. So, if I create, and actually, if I think of this as being morally something like, doing something, creating a field, a particle, or doing something like creating a particle at a given time and a given spatial location, then I've got, well, anyway, let me just say that I want to compute this. Ultimately, I want to compute this guy. So maybe, but the thing that's funny about this, before I actually get to this guy, because there's something funny, he doesn't have a nice interpretation the way that there was the analog in the relativistic case did, because he's got annihilation and creation operators in him. He's got annihilation and creation operators in him. So he's doing something much funnier than what happened non-relativistically. So, but this is ultimately what we want to compute. And this kind of has embedded in it a lot of the kind of physics of how things, anyway, all the physics can be recovered if you know this. But let's first recall the non-relativistic case. Okay. And so non-relativistically, I had this calculation. So there, what I was doing was I was computing the same thing, except something that made it a lot more. And when I write down the non-relativistic case, again, I'll just stick to one. For now, I won't do it for multiple space components, just for one space component, because it's easy to generalize. So then what happened is you had a field operator at T1, X1, and you thought of this guy as creating a particle or adding a particle, with a position X1 at time T1 into this state space, and then you had this other operator which was the adjoint, which had the annihilation part, and you computed what this guy was. Okay. And you could do this using, and again, I had this expression for what the field operators, time-dependent field operators were. I could just, in terms of these these ANA dagger annihilation creation operators for fixed momenta, and I could just go ahead and calculate this, and maybe and let's see. So anyway, I won't go through this calculation again. It's on page 400 of the notes. But you basically end up with what you ended up with was so you just had a contribution from the, anyway. So you use the A of P here. And you just use that, and you worked out this calculation, and then you ended up with this. You ended up with 1 over 2 pi, the integral from minus infinity. So this is an integral over the momentum space of P e to the minus I P x1 minus x2, and then e to the minus I P squared over 2m T1 minus T2. Okay. So if you do this calculation, you get this integral. And as I kind of pointed out, this is actually kind of a tricky gadget to work with. So there's a distribution. Okay. It's really not trying to integrate over P, this integration would just give you a delta function. But but this guy integrating this thing, which, as P gets large, this kind of oscillates faster and faster. This is really a kind of a bad news gadget to be trying to think about. So you have to think about what this distribution is. And then if you look at this calculation, I'd actually gone back and I'd done kind of similar equations way back when we talked about the free particle. So this kind of story, which is telling you that if you create a non-relativistic free particle, let it propagate for a while, what's it going to do? Well, that's just the same story as solving the free particle Schrodinger equation, and so going way back, you find that let me then kind of make it say it this way, that what you find. Oh no, this is where I want to. How did I want to say this? Okay. So this makes, so actually, to make sense of this, what you need to do is you basically need to go, you need to kind of turn this, integral over this infinite phase into something that's actually falling off. As p gets large, it's actually falling off. So what you want to do is you basically want to add a small imaginary piece to your to your time, and then that will then cause and if you do that with the right sign, that will cause this guy then will fall off exponentially, and this will become perfectly well defined. So you should make this integral well defined. I want to do this by taking the by taking by doing it for time complex. So you consider tau t plus I tau. Okay. And then what we're going to do is, and so this actually becomes well defined for let's see. So if you put t, if there's an I tau, then if tau is negative, so then what you want to do is take the limit of tau goes to 0 from the negative side. Okay. So in this, the way this is set up, for if I take time plus an imaginary piece, and then let it go to let this time difference be complex, and have a purely imaginary part. Now this integral is going to make perfectly good sense for tau less than 0, and then I can take the limit. So let me maybe draw something in the t and tau. So z is t plus I tau. So this is going to make this integral is going to make sense. This integral is going to make no sense over here, but it's going to make sense here. And then you want to get the t values, you want to take the tau goes to 0 from the negative side. That's the idea. Okay, and then so I actually worked this out in the and so what you find is that anyway, what you find if you look at this expression, so if you actually took time to be purely imaginary, then what you would have is you would have an e to the minus, you'd have no I, and you'd be integrating a Gaussian e to the minus p squared 2m over 2p. So you'd just be doing a Gaussian integral. So for time purely imaginary, this is actually perfectly well-defined problem. It's actually the problem of the heat equation. But in general, so you've kind of got you've got the heat equation along here, and you've got the Schrodinger equation. Along here. And it turns out, and everything, if you know something about analytic functions, it turns out all the behavior of this guy is kind of holomorphic on here. So if you know what's happening here, you can analytically continue to the boundary. But something really kind of funny is happening along here. And if you try and just kind of write down formulas and work at at real time, you've kind of written down something which you don't actually know how to make sense of. You have to do something. Okay, so that's the non-relativistic story. Now let's do it for the Klein-Gordon case. Oh, and if you do it, yeah. Anyway, let me know right then. But you can then go down. You can actually compute this guy, and you get a perfectly. Anyway, you get the standard story about the free particle propagator, which we talked about back then. But now let's go and see. Let's go and see what happens for the Klein-Gordon case. Anyway, let's just say the relativistic case. So the relativistic scalar. So we want to compute this guy. Let's do. I mean, so this guy's going to be translation invariant, and he's only going to depend upon the time difference of these two operators or upon the spatial differences. So what you can do is you can compute case. So let's compute. I think I call it this U of t x vector, and then 0 and 0 vector, which is just to simplify the calculation. I'm going to just take one of these coordinates to be fixed at 0, and then let's see what happens at that and any other coordinate. Anyway, so you do the calculation, and so we know what these operators are in terms of these nice standard annihilation creation operators A and P, and let me just kind of start writing down this calculation. I may abbreviate some of the details. They're in the notes, but it's basically there's a 1/2 pi cubed, and then you're integrating over. You've got two R3 integrals. One for each field, and then you've got your 0, and you've got your first field is at a p vector e to the minus I omega p e to the I px x vector, and then there's an a dagger of p vector. And I'm worried that at some point I keep on. Anyway, I hope this is correct. This guy, and then you're going to multiply him by a dagger of p vector prime plus a dagger p vector prime. So this is just the field at time 0 and x equal to 0. And then you have to integrate. There's a d cubed p vector and a d cubed p vector prime, and you got a square root of 2 omega p vector and square root of 2 omega p vector prime. Okay, but then what you're going to do is just use the commutation relations for a and oh, okay. Oh, sorry. And the other thing that happens is here. This is acting on 0. Okay. So these guys acting on 0 give you 0. So you just have to worry about the term where this guy acts here and this guy acts here, and then you can use the commutation relations for these guys, which give you those give you a delta function in t, and so you then end up with 1/2 pi cubed R3 e to the minus I omega p vector p. e to the I p vector of x vector. So this delta function you're going to get just turns means that p vector and p vector prime have to be the same thing. So you just get one integral. These square roots go together, and you just end up with this. So this is the analog of in the relativistic theory of what I had in the remember. So I had written down in the So this is similar to the story that you saw in the non-relativistic case. There, I just had one p, but here there's just three p's. The things that are different are here. So this guy, instead of being p squared over 2m, he's the square root of p squared plus m squared, and there's this guy. So you don't have a and actually, in the limit of anyway, but so this is formally somewhat similar to the thing that I wrote down before, but it's got these two different features. Okay. Oh, and one thing to say about this is remember that this thing should look again. If you look at this, you should say, wait a minute, this thing is supposed to be Lorentz invariant, and there are Lorentz transformations here, but it doesn't look Lorentz invariant. But again, that you can see that this is actually, by inverting the trick that we used before, you can see that this is the same thing. I could have also write this as 1 over 2 pi cubed theta p0. So now I'm just integrating over the positive energy mass shell of delta of p squared. Yeah, anyway, delta of it's the same. It's actually p squared plus m squared. This thing. So it's minus the energy squared plus the spatial component squared of the momentum plus m squared, and then e to the p0 t. Right. Okay, and this is the thing that I also could write e to the IPX. So this is a nice Lorentz invariant expression, and he's basically saying that that this guy. So what this guy is that he's really the Fourier transform. So here's the transform of delta on the positive energy mass shell. Okay, so in energy momentum space, remember there's this thing. Okay. And so you're basically integrating over energy momentum space, and you're just taking taking the distribution which says restrict your function to the positive energy mass shell, and you're taking the Fourier transform of that. That's really what so this is the relativistic thing. Okay, now let me say a few words about it. So a couple of things about this. So this is actually kind of a tricky. Let's see what I want to. Yeah, let me say. So again, let me say a few things about this expression, and then I won't quite finish because there's a few other things I wanted to kind of point out, and which we'll get to next time. So what is so this has the same. Let me leave this here. So again, this is the same problem as in as non-relativistically. And this is a distribution. I mean, it's the same kind of problem. I'm trying to integrate. I'm trying to integrate off to infinity these kind of things, the things that don't decay at infinity. Right? I mean, I can go off arbitrarily far in p space. I've got this phase factor that's just varying more and more wildly. So this is actually this is showing this is not in any sense a well-defined function. See, one thing you could do with it. I have this. Okay. Oh, actually, maybe one thing I can say. Well, let me say this. You can do some more work and get something like a slightly more explicit formula for this. You also can note you can if you can do some of these integrals and play around with them and relate them to a certain special function, and then you end up with that this is equal to the m over 2 pi, the square root of x vector squared minus t squared. Then now k1, so k1 is some modified Bessel function of some kind, and then it's m square root of x vector squared minus t squared. Anyway, so if you go and look up the definition of this special function as integral, you see you could show that it's this guy. I won't do that. But then but what I wanted to explain is that so you can make sense of this by taking t complex, then a limit as t as imaginary part goes to 0. Okay, but you have something much funnier going on than what happened in the non-relativistic case. And what you have is this: if you look at what this function is doing as a so at fixed x vector. So if you take x vector to be something fixed, and then look at the dependence and just look at the dependence in t, what you find is this. Okay, so this is t. This is what I'll call tau, and then t. So there's a complex variable t plus I tau. So in other words, you just look at the anyway. This becomes a fixed number, and t becomes a complex variable. And you try and you get a perfectly you get an expression you can make sense of, except it's got some funny things that are happening due to this. So something funny is happening with the square root as the square root goes negative. So here at x vector, and here at minus x vector, something funny happens. And what happens is that for this for t less than this, it's perfect. This thing makes perfectly good sense in this region here, but it does something. You get a problem if t is bigger than t squared is bigger than than x squared. If t is bigger than x squared, and so and you also get it here. And so what's happening here is this corresponds to t to the, you've had time t less than x, and so this is actually the space-like region. Okay, so you're fairly far in x, much farther in x than you are in t, and so your space like separated. So you're causally disconnected. You're no way to get a signal to there. From this guy's called the space-like area, and then this part is called the time-like, and you get a and what happens here? This is, if you studied any kind of complex variables, here you have what are called branch cuts. You can, if you know the function on one side here, you can analytically continue it over the other side, but you're going to get something different depending which direction you go. So what happens here is you have to define define your propagator as the limit as imaginary part goes to 0, but it depends on which direction. Okay, so let me. I think maybe I'll start say some more about this next time. But this is the anyway. This is kind of why this is actually a much. I mean, the free particle expression for the propagator in the non-relativistic case is already a fairly tricky distribution to make sense of. You have to, but there's only kind of one way to make sense of it. The problem with this thing is that there are different ways. You actually can make sense of it by coming in different directions, and then what you have to do is you have to then figure out. So the standard thing people then do is say, well, to get something physically sensible to happen, I'm going to take the limits in a certain specific way, and this kind of goes back to Feynman. And you have to, and there's always some long song and dance at any point in a quantum field theory book when you get to this calculation. So let me kind of go back, say that, back to that next time. I think the only other, okay, yeah, and then just some other things to notice is other thing to note, which maybe I'll start with next time, is note. So it's well defined for space-like. So in this region, it's not a distribution that you have to do anything funny. It's just a well-defined thing, and it falls off. Anyway, you can I don't know, maybe I'll say something about that next time. But it's a perfectly well-defined function in here. And this is something kind of, and this is actually bothersome, because what you're doing, remember, is you're saying, phi 0 0, p x vector. So I mean, if you want to interpret this thing as being, I'm creating here and annihilating here, you're in danger of having some, if two things are space-like relativistically, there's kind of a principle of causality that they're not supposed to know about each other. There's not supposed to be any way to send a signal between these two guys or doing like this. But this guy actually, the fact that this guy actually is non-zero here is, it starts to make you realize, wait a minute, there's a problem with this interpretation of creating a particle here and annihilating it here, because if that's all that's going on, then I could send this. I could send a signal, you know, in a outside the light cone in a space-like way. So something else is going on. And so I think I better, maybe I'll stop here and then pick that up next time and maybe say a little bit more about this calculation. Okay. Okay, so any questions about this? I don't think, so I haven't quite finished what I want to say about kind of two different topics. One is about the symmetries and the other is about the propagators, but I think next time I'll try to finish up both of those.
Is there maybe like a quick summary of you that you can say of what happens or how this is resolved?
Okay. Oh well. It turns out physically, if you think about it, what actually happens is that Tx. It is equal to 0 for space-like. And so it turns out if you actually think about what you would have to do to send a signal between these two things, you'd have to kind of anyway, you would need some non-zero commutation. The fact that these two things commute is going to be the explanation, and the fact it's kind of exactly so. Anyway, so the general principle that you need in any kind of relativistic field theory that's not going to violate causality is that, you know, operators at two space-like points have to commute. They don't know each other about each other, so you should be able to simultaneously diagonalize them, and so they should be, you know, they're physically independent things. So the general principle is that, you know, even in an interacting field theory, we believe that any operators at space-like points have to commute, and you know, and it actually works out here. But the way that this works out is not what you might expect by this being 0, but by, you know, this guy is non-zero, but if you compute him in the opposite direction, you get the same thing with a minus sign. So this is kind of telling you that, you know, something funny is going on. I mean, this is not just I mean, if you want to try and interpret this as some kind of some kind of propagation of a particle forward in time, that you really need, there's really kind of some canceling particle going in the opposite direction. That's what I was trying to say a little bit last time. I mean, this has to be doing something more complicated than just propagating a particle in time, because otherwise you're not going to get 0 here, and this is you're going to have trouble. So the reason, this is kind of, again, it's reason why you have to have both annihilation and creation operators built into this guy. And so what's happening is something trickier involving degrees of freedom that, depending upon which frame you're looking at them, they're moving forward or backwards in time, and they're annihilating or creating. And it's a confusing situation, but that's I mean, mathematically that's the resolution that you can.
So I guess physically the resolution is just that they don't have the correct interpretation as just creation at a space-time point and annihilation.
Yeah. So I mean, or it's more that if you try and think of it in that language, then you have to think of it as creating a particle and creating something moving forward in time and something moving backwards in time in such a way that if you do it in the opposite direction, it's going to cancel when you're space-like. I mean, you can. I'm trying to remember. I think Feynman in one of his books or early papers, he was clearly kind of very, very much thinking in this language, he was trying to think of all these these calculations as corresponding to particles propagating. And so he had some kind of, but he kind of realized you had to have some picture of things that could either move forward or backwards in time, and that with different amplitudes, and then the amplitudes had to cancel. And again, to make this more complicated, what I'll say next time is that if you have if this is not a real scalar field but a complex scalar field, then the particle and the antiparticle are two different things, and yeah, anyway, and then it becomes much more a much more kind of, anyway, well, in some ways more confusing, or in some ways more straightforward, that you really can tell the difference between what's a particle and what's an antiparticle. The problem with a real scalar field is there really isn't, they're really the same thing. A particle and antiparticle are the same thing. So if you try and kind of start using the language of particles and antiparticles, you get confused. Okay. Anything else? Okay, so let me shut this off for now. But if you again, please, I'll be around for a while. Please come back and ask me if there's anything else you'd like to talk about. Okay. Okay. Bye now.
Thank you. Thank you.